So last time we talked about how quantum mechanics tells us that the component of the angular momentum along any axis that you choose to measure is quantized in units of h bar. And so we showed that that means that the rotational kinetic energy is also quantized, and that the smaller the moment of inertia, the bigger the energy spacing between those quantum levels becomes. In particular, that means for a diatomic molecule, where the moment of inertia for rotations around the symmetry axis of the molecule is really tiny, the quantum level spacing is gigantic, which means that effectively you're always in the ground state for those rotations, and that rotational kinetic energy doesn't contribute to the heat capacity. We talked about how to use the equipartition theorem to estimate the heat capacity. And essentially what we found was that every term that is proportional to a position squared or a velocity squared gives you a factor of 1/2 cap R in the molar heat capacity. So applying that to diatomic gases, we got this graph where we're graphing the molar heat capacity at constant volume. That's what this little V means, as a function of temperature. So at high temperature, all these terms are active except for rotations about the z-axis. So we've got 3 terms associated with translation, 2 with the vibration, and 2 with rotations about the x and y axes. So at high temperatures, the molar heat capacity is 7/2 R. As we cool the system, first we get to the regime where kBt becomes comparable to the energies associated with vibrations, the quantum level spacing associated with vibrations. So those terms freeze out, and the heat capacity goes down to 5/2 R. And then at a lower temperature, kBt becomes comparable to the level spacing for rotation. So those terms freeze out, and we get down to a final value of about 3/2 R at very low temperatures. Then we started talking about modeling a solid. So in our model, each atom is connected by spring forces to the surrounding atoms, and so it vibrates back and forth in the x and y and z directions. So let's say for the x direction, there would be 2 terms in the energy. This one is proportional to a v squared. This is proportional to a position squared. So each of these 2 terms at high enough temperature, at least, is going to contribute 1/2 R to the heat capacity, and there are 6 terms, so a total of 6/2 R at high temperatures. We also briefly said, I didn't prove this, I just stated it, that the quantum level spacing, the quantum level spacing for vibrations is given by h bar omega, where omega is 2 pi times the frequency of the vibrations. So questions about any of that? Okay. So let's talk a little bit more about the heat capacity of solids. And I just want to, so again, if we start by looking back at this graph of diatomic molecules, as we're going, let's say, from 7/2 R down to 5/2 R, there is this transition region where the vibrational modes are freezing out like this. So at temperatures above this, we're in the regime where kBt is much greater than the quantum level spacing. Temperatures below it, it's less than. So if I draw the quantum level spacing for vibrations, here we're in the ground state, and here we're in the first excited state. So if we're in a regime where kBt is like this, so I'm going to call this kBt sub hot, so this is some fairly high temperature, then it's easy for the system to get out of the ground state up to the first excited state, or even the second, third, fourth, fifth excited states. So it can fairly easily get that. If instead we're at a lower temperature, kBt cold, then the system is more or less stuck in this ground state. And so it's as if this degree of freedom doesn't exist, or basically it's always stuck in the ground state of the vibration, and so therefore the vibration doesn't contribute to the heat capacity. So if I were to, I'm going to regraph the diatomic heat capacity at constant volume for diatomic gas. And in this case, I'm just going to concentrate on that top part. And instead of the horizontal axis just being temperature, I want to think of it as kBT divided by the quantum level spacing, delta E. So I'm just changing the scale a little bit. But as long as delta E is fixed, it doesn't really change the shape of it. So again, you're starting off at this higher value and you're freezing out, and we're not going to worry about the lower temperatures for now. So what I want to point out right now is that as you move to the right on this graph, so that is as you're making this kBT over delta E bigger, it's easier for the system to be promoted from the ground state out, and that therefore the vibrations start to contribute. You can move to the right on this graph either by increasing kBT or equivalently by making the quantum level spacing smaller, which also makes it easier to jump out of the ground state. Questions so far? Okay, so now let's apply that same thinking to a solid. We argued last time that the heat capacity constant volume for a solid at high temperatures is equal to 3R. And so we're going to make a similar graph of the heat capacity as a function of kBT divided by the quantum level spacing. And so at high temperatures, it's equal to 3R. As we lower the temperature, those vibrational, this is all due to vibrations, because the atoms in a solid cannot translate. They're more or less fixed in place, so the only energy they have is vibrations. And so as we lower the temperature, this is going to reduce down to, in this case, to 0, because that's the only energy in the system, is the energies of vibrations. And again, you can move to the right on this graph either by increasing the temperature or by decreasing the quantum level spacing. So increasing the temperature, you could do that with a single sample. Decreasing the quantum level spacing, you'd have to do that by moving from one material to a different material. Does that make sense? Okay, and I want to remind you that the quantum level spacing for vibrations, I didn't prove this, but I stated it, is equal to h bar omega, where omega is 2 pi times the frequency of vibrations. Next week, we're going to talk more in detail about vibrations, and we'll show that the angular frequency of vibrations, omega, is equal to the square root of the spring constant, K, divided by the mass of one atom. So again, here's our model of the atom and its surrounding atoms that it's connected to by springs, and the K here is characterizing these springs. Okay, so now I want to see, can you synthesize all of this and make a prediction? What I want you to do is to compare the molar heat capacity at constant volume for diamond to the molar heat capacity at constant volume for gold. AU is the abbreviation for that. So bigger than, less than, equal to, or maybe you don't have sufficient information to tell. But I am going to ask you to make use of stuff that you know in general and that an ordinary high school student might know about gold and diamond. So I'm about to assign you to breakout rooms. Before I do that, are there any questions? So again, I want you to use these ideas that we've just been talking about use this graph. So make sure you've got this in your notes, including that the horizontal axis we're thinking of as kBt divided by the quantum level spacing. Use this equation and this equation. Okay. Assign the rooms. Let's see, Ariana, can you walk us through it, please?
Yeah, so we were looking at the equation omega equals root k over m. And we were talking about the difference in spring constant between diamond and gold.
Uh-huh.
And we said that diamond has a higher spring constant
And why did you say that?
because it um like diamond is really strong, and that means like the solids, a strong solid is like super compact,
So
um
I just want to clarify your language a little bit.
hard.
So there are different ways in which things can be strong. Um, so diamond is really hard, so meaning you can't scratch it very easily. And so, but as Ariana has said, that means that it has a high spring constant. Go ahead.
So if omega, so that would make its omega larger for diamond than for gold.
Okay.
And if it has a larger omega, that means the delta E will be larger, um,
Okay.
which means it will have a lower heat capacity because um, a, a larger delta E. Yeah.
So if we're looking at this graph, larger delta E means that this quantity on the horizontal axis is smaller, so we're moving to the left, meaning that the modes are at, let's say, room temperature might be here for diamond, so the modes are mostly frozen out, whereas it might be here for gold, meaning that the modes are only a little bit frozen out. And the T room is in different places on the graph because the delta E's are different for those two different materials. Questions so far? So Ariana did a nice job of explaining the difference in K and its effects on the heat capacity. Can somebody else tell us about the difference in M and how it affects the heat capacity? Let's see, Matt, you were all by yourself, but maybe you still could take a stab at it. Which one has the higher M, diamond or gold?
I'm not sure.
Okay, that's fine. Somebody else, which one has the higher mass if we're thinking about one atom of diamond or one atom of gold?
Gold.
Yeah, so gold has atomic mass of about 197. Diamond is made from carbon, which has atomic mass of about 12. So it's quite a big difference in the atomic mass. So the diamond has the lower atomic mass. That also means that diamond has a higher omega. So both effects are working in the same direction. Both the stiffness of the diamond and the lower atomic mass are making the omega higher. That's the angular frequency of vibrations. That means that at room temperature, KBT is smaller compared to the quantum level spacing. And so those modes are more frozen out and the heat capacity is lower. Okay, so let's compare our prediction with the actual experimental data. The molar heat capacity at constant volume of diamond is 6.37 joules per mole Kelvin, whereas the molar heat capacity at constant volume of gold is much higher, 25.6 joules per mole Kelvin. So in accord with our prediction that at room temperature, though the vibrational modes of diamond are more frozen out, so its heat capacity is lower. Okay, so now let's ask another concept test. I don't think I'm going to put you in breakout rooms for this. I'll just give you a moment to think about this. Let's compare the heat capacity at constant volume, the molar heat capacity of diamond Scott, can you mute yourself? We're getting a little bit of feedback, or maybe it's Marissa. I'm not sure which.
I'm sorry about that.
Thank you. Let's compare diamond versus graphite. So graphite, as you may know, like diamond, is made out of carbon atoms, but whereas diamond is a very stiff material, graphite is a rather soft material. That's what your pencil is made out of. So which one has the higher heat capacity? Think about that on your own. Okay, who would like to take a stab at this? Go ahead, Allison.
Well, graphite is still carbon, but it should have a much lower K because it's much squishier than diamond is.
Good. So lower K and omega equals square root K over M. So that means, go ahead.
Which should mean that does that mean that the W is higher than diamond?
No, because the K appears in the numerator inside the square root. So It's going to be a smaller omega. And that also means it's going to be a smaller delta E. So what does that mean about the heat capacity? So if we look at our graph here, delta E is in the denominator. So if it's smaller, that means you're moving to the right. So it's a larger heat capacity. It's sort of similar. Graphite is similar in comparison to diamond as gold is softer. So it's going to have a larger heat capacity. And again, it's larger because since the delta E is smaller, fewer of the atoms are stuck in the ground state, because with the thermal energy available at room temperature, they can get out of that ground state more easily. And so that energy matters and contributes to the heat capacity. Good.
Could you explain that again?
So if I were to compare the energy level diagram, so here's diamond, the energy level diagram for the vibrational modes in diamond. Here's the ground state, here's the first excited state, here's the second excited state, and there's other ones up there. And KBT is maybe, let's say, this much at room temperature. So at room temperature, it's quite rare for an atom to be able to get out of the ground state. Almost all of them are stuck in the ground state, so they're not vibrating. Or if I want to be a little bit careful with my language, they're vibrating only with the energy of the ground state. So it sort of, they all have a fixed amount of energy. And so it's as if they're unable to vibrate, basically. Whereas for graphite, these levels are much closer together. So it might be like this for graphite. And so now with this amount of room temperature energy available, some of them, so it's on average, that's the energy they have. Some have more than that. And so there's a much bigger fraction that can get out of the ground state up to the first excited state or even the second excited state. And so that energy matters and counts in determining the heat capacity. Good questions. Okay. Let's now think about liquid versus solid. And let's think about the molar heat capacity of ice versus water. Now this is a little tricky, right? We haven't talked at all about liquids before. We've talked some about gases and some about solids. So I want you to try to use the same kinds of ideas that we've been talking about so far and try to figure out which of these would have a higher heat capacity. All right, I'm going to go ahead and assign you to breakout rooms, and I'll make sure that Matt is not stuck in a room by himself. He should be good, I think. Go ahead and move to your room.
Yes.
Okay, can you walk us through it?
Sure. So I was just thinking that water, since it's a liquid, would have a higher heat capacity because liquids have more different types of energy than solids do because they're not as confined. So you could think of it as having more 1/2 kBt terms added up because you have all the different translational energy terms from the equation that we were looking at last class, and that translates to larger heat capacity.
Good, exactly. So in ice, every atom, the only kind of energy that it can have is vibrations. Whereas in water, you still have these molecules, so they can, and each of the molecules is still sort of bound to the other molecules. So you can still have vibrations, but then in addition, you've got translation. So there's sort of more ways to move. Every way that you can move gets a 1/2 kBt of energy. And so that means a higher heat capacity. And in fact, it's about twice that of the heat capacity of ice. And that should also sort of make sense in the freezing out way of thinking. Literally, in this case, we're freezing things out. So as you go from water to ice, you're freezing out those translational modes in this case, leaving only the vibrational modes. Good. Now, often in everyday life, you are experiencing heat capacity of things not so much in terms of the molar heat capacity as in terms of the specific heat. And I want to remind you the specific heat is the heat capacity divided by the mass, or we could write it as the molar heat capacity divided by the mass of 1 mole. And so now I want you to think about, well, I don't think I'm going to pose it as a concept test, but the mass of a mole of diamond is much less than the mass of a mole of gold because the atomic weight of diamond is so much less. And that's appearing in the denominator. And so that actually flips the comparison. So if we think about the specific, we saw that the molar heat capacity of diamond was much smaller. But when we think about the specific heats, that for diamond is equal to 630 joules per mole Kelvin, whereas that for gold is only 129 joules per mole Kelvin. So the specific heat of diamond is bigger, but the molar heat capacity is lower. Okay. Now, when you are talking with physical chemists or with physicists about heat capacity, they're almost always going to start muttering about this heat capacity at constant volume, which is what we've been talking about so far. So for example, we had a box that was filled with gas and we don't allow the gas to expand. They're muttering about that versus the heat capacity at constant pressure. Heat capacity at constant pressure. So where you allow the volume of the sample to change when you add the extra heat to it, but you keep the pressure applied constant. The heat capacity at constant volume we've seen is relatively easy to calculate, at least in the extreme high temperature, using the equipartition theorem. So this is in general the one that's easy to calculate, but it can be difficult to measure heat capacity at constant volume, especially if you're talking about a solid or a liquid. Because if you imagine doing the experiment, when you're measuring heat capacity, you add a well-known amount of heat to something, you measure its temperature increase. When you do that with a solid, it wants to expand, and it's really hard to keep it from expanding. You can, if you exert enough force on it, you will keep it from expanding, but it takes a lot of force. And so it's much easier experimentally to do things at constant pressure, because after all, we're in the atmosphere, which is exerting a constant amount of pressure on everything. So this is easier experimentally. Just as a kind of interesting aside, I always used to think, and just until like a couple of years ago, that, because I think in this class we're not going to have time to talk about thermal expansion, but you guys know that when you heat things up, most things expand. And so I was fascinated, I'm kind of a train buff, by welded train rails. So if you look at a normal rail for a train, there are these lengths of the railroad rail that have joints between them. And so when the rails get hot, there is space for them to expand into. And when you drive across a bridge, you will often see this kind of a pattern of teeth that are almost meeting but not quite. So there's a little bit of a gap that you have to drive across. And when I was a kid, that always used to really freak me out. But of course, it's only like a half an inch or something. It's not a problem for your car. But that way, when the road expands thermally, there's space for it to do that. But if you look at the rails, like at our Haverford railway station, they don't have those gaps. They're just continuous. They're welded. So there are weld joints here, but it's continuous metal. And so for a long time, I was confused about what happens when it gets hot. And if you look from above, so finally I got a chance to talk to a railway engineer, there are these little plastic clips that are spaced really close together. They're spaced, I don't know, maybe 4 inches apart, that are holding the rails in place. And they're keeping it from bowing because of that expansion. So it's basically not being allowed to expand. If you exert enough force on it, it doesn't expand even when you heat it up. But it takes a lot of force. Okay, and of course the reason that it's nice to have welded rails is it gives you a much smoother ride. And I don't think I've ever ridden on the Acela, But if some of you had, in order to go as fast as that, you have to have welded rails. So there are welded rails all the way from New York down to Washington. Okay, back to CP versus CV. So it's important for us to understand how to convert from one to another. For gases, it turns out to be pretty easy. So let's consider the following situation. We're going to have a cylinder, and there's a piston that floats on top of, here's some gas, and there are seals. So this is a piston. There are seals on the sides that prevent gas from getting past the piston. So we could push the piston down and compress the gas and it wouldn't get out. When we look from above like this, in that view, the cross section is round and the area of the piston, we'll call it A. So we want to compare this situation versus the situation of an equal volume box that doesn't have a piston and where the volume is going to be fixed. And for both of these, I'm going to add the same amount of heat into them. In the case of the piston, when I add this heat to it, we know that PV equals nRT. I'm keeping R constant, of course, and N, the number of moles, is being kept constant. So if I increase the temperature, that means that the pressure is going to increase and it's going to push upwards on the piston. So some of the energy that I put in, some of this delta Q, is going into work pushing that piston up. And that is fundamentally what causes the difference between a heat capacity at constant pressure and a heat capacity at constant volume. So we're going to start calculating how much work is done on that piston by the gas. And we'll use that to find the conversion between CP and CV. So work done by gas on piston. So when we add that small amount of heat, it's going to push the piston up by a small amount. We're going to work with really tiny amounts, so let's call it an infinitesimal amount, dx. So the work is the force exerted by the gas times that displacement. The force, in turn, is equal to the pressure times the area, right? That's the force. And we still have that factor dx. Now we're going to use PV equals nRT, the ideal gas law. Oh, wait a minute. I'm getting ahead of myself. So let me just, before I use PV equals nRT, let me recognize that A times dx, that's the change in the volume inside underneath the piston. So we could write that as dV. So putting that all together, the work done by the gas on the piston, it's an infinitesimal amount of work, so we'll call it dW, is going to be equal to P times dV. Now we're ready to use PV equals nRT. Again, we're keeping the number of moles fixed. So when we change V, the only thing that can change on the right side is the temperature. So P times dV is nR times dt. And so we could substitute that in here to get that dW equals nR dt. Okay. You guys should be grateful to section 1 because due to all the questions that they asked, I was able to explain things to you guys much more clearly than I was to them, but I don't want to get ahead of where we got in section 1, and this is where we were able to get to. So, are there any questions right now?
When you put arrows up under the PV equals NRT, what does that mean?
I was just talking about different things, so it doesn't mean anything.
Oh, okay.
So, yeah, you should cross those. Those are not meaningful. How do I erase them there? So, other questions? Okay, then that's it for today. Have a wonderful weekend.